This is the video that we promised for those who are not quite familiar with the Bellman-Ford algorithm. The Bellman-Ford algorithm determines the cheapest route through a graph. More specifically, it considers a graph where the edges have certain weights associated with them, and one wants to find paths that link every node to every other node, or in the language of graphs, every vertex to every other vertex in the graph. The algorithm is significant in the sense that it can handle negative costs, which the Dijkstra algorithm cannot do at all. However, this only applies when one has a directed graph or a digraph where the negative costs are associated with a link going in one direction. In fact, if one has a negative cost that forms a loop, then one can go around the loop all the time, and that would push costs down forever and ever. So especially where we consider a network where the links are bidirectional, we will not be able to use negative costs at all. The algorithm was first discovered in the mid-1950s by a certain Alfonso Schimbel. However, the publications shortly afterwards by Bellman and by Ford, who independently discovered the same algorithm, became much better known, and the algorithm is therefore named after them. Moore also discovered the algorithm independently about a year later after Bellman and Ford, so some people prefer to add his name to the list as well. However, in most cases, it is simply known as the Bellman-Ford algorithm. From a networking perspective, the Bellman-Ford algorithm is significant because it works in a distributed manner inherently. One only looks at a specific node and communication from neighbors from that node to get the algorithm to operate. Hence, there is no central party that determines routes, and there is no need to know the topology of the network before one starts to determine routes. There is also an ability inherent in the Bellman-Ford algorithm to adapt to changing conditions. In that sense, it is dynamic or adaptive. In the video, however, we will only make one very brief remark about this feature of the algorithm, and we won't go into any details whatsoever. Our approach will again be one where we work through an example, and hopefully the example, while it does become a bit repetitive at times, will provide viewers with the opportunity to discover how it works by going through the same steps on a couple of occasions, and then also by encountering a couple of conditions that one needs to look out for when applying this algorithm. So let's dig in and look at our example. For this example of the Bellman-Ford algorithm, we will use the same network that we used earlier to illustrate the Dijkstra algorithm. We need to get some space so that we can move some routing tables in. Remember that for the Bellman-Ford algorithm, there is no overall view of the network. Everybody has a local view of what's going on. So initially, node A will simply know that it has two neighbors, B and F. And if it wants to send something to B, it can just give it to B, and the cost will be 1. And if it wants to give something to node F, then A can simply give it to node F, and the cost will be 5. Similarly, if we were to look at node B, then B has neighbors A, F, and C, and you can see that reflecting in the routing table that it initially compiles. How to get to its neighbors, and it would be at a cost of 1, 8, and 1. That is exactly what you see there. Node C will do exactly the same. Node C will calculate its routing table based on what it knows about its neighbors. Note that it's very important here that the Dijkstra algorithm spoke about the prior node. Here the question is always, who do we give this to next? So we can now continue and compile all the initial routing tables for all 6 of the nodes in this network. It's going to be pretty boring, so these 3 will suffice. In fact, what we want to do is we want to see what happens when we begin to exchange routing tables. Now, this is the sort of thing that makes the Bellman-Ford algorithm rather hard to illustrate, because these exchanges occur amongst various routers on the network. So one doesn't really know who is exchanging at what moment with whom. And therefore, we're going to follow a sort of systematic approach, although that is very unrealistic. We will assume that A shares its routing table with B, and then B shares its routing table with C, and then C shares it with D, and so on. So initially we have the routing tables of A and B as we've just calculated them. As a reminder, the cost to move between A and B is 1. So if A can get somewhere where B cannot get to, then there will be an initial cost for B to get to A, and then whatever cost A reports. That's why whenever we carry these costs forward to B, we have to add 1. Now let's do that, and what you can see here is that we have taken this routing table, and for this example we've simply copied it down here. There you can see that the next hop for what we've learned is A, so B will give whatever it wants to send to those 2 nodes to its neighbor A, and its neighbor A will then send it at a cost of 1 or 5, but there will be an additional cost of 1 to give it to neighbor A. That gives us a nice routing table to work from, but you can see that there are some problems in this routing table. The first problem is the one that is pointed out there. It is the fact that at node B, we have now determined a route to get back to B at a cost of 2. However, if you are at B, the cost is 0. You're probably not even going to record it, but if you want to record it, you will record it that if you want to go to B and you're at B, the cost would be 0. So that needs to go. We don't want that in the table. It's unnecessary and it's gone. And then we can see another problem that exists in this routing table. We have 2 entries for F, and we can only have 1. So there is an entry that will cost us 8 units. There's an entry that will cost us 6 units. So the easiest is to just wipe out that one that will cost us 8 units, and we are left with the cheaper one. In the meantime, we can forget about what table A says. We are happily working on node B's table. Node A has nothing further to do with us. In fact, the moment that we received A, we already forgot about it at B. We just recorded the information that we received. So clearing that space gives us a nice compact table, and we can now begin to look at what we have in table B so that we can share this with table C. Just before we do share this, remember that table B used to look like that. If you didn't make a note of it, you may want to go back and look at what it looked like initially. But what this illustrates here is how we have learned something at node B. Initially, the cost to get to F was 8 units. Now we can do it at a cost of 6. So we have arrived at a cheaper cost. Whether that cost is optimal, we don't yet know. We will have to run this algorithm until it converges, until we don't learn anything new from our neighbors. However, it may be worth reminding you that the Bellman-Ford algorithm is one that works for adaptive network conditions, so we may find that the costs do increase over time. Now, we're not going to look at that, but what it will mean is if we suddenly see a node reporting a node that we thought could do it at 6, suddenly reporting a higher cost, then we have to increase our cost. As noted, we're not going to do that. We are simply going to use B as it looks now, and we want to send it on to C. Routing table for C looked initially like that. However, we want to update C with the information that we've learned at node B. So we're going to forward the routing table at node B to node C. If you think back then, the cost to communicate between B and C was also 1. Hence, we have to consider the same cost increase. In other words, if we want to use any cost that we have at B, then we can tell C that it can send it to B and use that cost, but it has to pay an additional 1 unit. Sharing this information takes us to a table where we have included all the knowledge that we had at B. So at B, we could get to A, C, and F, and there we can go to A, C, and F, and those brownish ones are the new ones that have been included. You can see this additional 1 unit of cost that we've added, and the costs were 116. And here we have it 116, and the new updated cost appears on the right-hand side. Now, the moment that we've shared this information, we can forget about what happened at node B. We will still keep its routing table up there for a while if you want to refer to it, but pretty soon we will drop it. What we rather want to do is to look at our table for node C. So node C will do this. There's nobody in a global position doing this. This is distributed processing, and every node processes its tables at its own location. It only gets the tables from neighbors as inputs. The moment we start inspecting this table at node C, we see there is a problem. It's telling us that we can go from C back to C at a cost of 2. No, if we're at C, we don't have to pay anything to stay at C. The cost is 0. So that's pretty useless information. We can wipe that. We end with a table that has all these entries. Now, the interesting thing is, at this stage already, node C is able to get to A, to B, it can remain at C if it wants to, it can get to D, it can get to E, it can get to F. So only after these few exchanges, we have the possibility to route from C anywhere. However, at this stage, the costs may not be optimal yet. Now we have a nice routing table existing at node C, and we can consider moving or passing it to node D so that node D can update its routing table. As a reminder, the cost to transmit anything between C and D was 1. That is why we have indicated the cost there as a +1. What this means is if D wants to use any of these costs, any of these paths that C knows about, then it can simply pass the message to C, and C can get it at those destinations at the indicated costs. So all of those costs +1 are available at node D. There is the table where we've added all these costs. So if we want to get to A, then we can just ask neighbor C to do that for us. The cost at which C can do it is 2. However, there is a cost of 1 to get it to C. So here we had 1, 2, 3, 4, 5 entries. we've added 1, 2, 3, 4, 5 entries, and for those 5 entries, we just copied the cost in all of those cases, but we also added the additional cost of 1 to get it to node C so that we can use node C's knowledge about how to get to those eventual destinations. The table, as expected, contains a number of problems. The first problem is the one that we've seen so often. This routing table now tells us that we can get to D at a cost of 2, but we are at D. We don't have to pay to get to D. There's zero cost involved. So we have to get rid of that entry and it is gone. That is, however, not the only problem. Here we have 2 possible ways of getting to E. And the one will cost us 2 units and the other one will cost us 4 units. So we need to get rid of the 4 cost because 2 is much cheaper than 4. And that is gone. And we can now collapse our table and we have our nice new routing table at node D. It is time for us to bring in the routing table at node E. Now remember, these are the initial routing tables. Our example is not convincing in the sense that the sequential updating of routing tables is not realistic. However, as we said earlier, it's hard to be realistic when things are happening asynchronously in parallel and nodes may be passing routing tables to one another and get their routing tables updated. So what we have here for node E is just its initial routing table, the one that only contains information about the neighbors of E. And we now want to add the information that we have in this table to the table at node E so that E can also learn about better options. As a reminder, again, the cost between D and E was 2 units. So we've indicated that by a +2. Again, this means if we want to get to any of these destinations using node D's knowledge, then we can simply send a message to node D, and node D will use each knowledge to get to the eventual destination. However, to get it to D will cost us 2 units. So where we've copied these costs, we have in all cases indicated that it is 2 plus whatever the cost used to be. So the cost to get to A, there is an option we will ask neighbor D to help us out, but to get to neighbor D will cost 2 units, and then neighbor D will be able to do it at a cost of 3. And the same for all 1, 2, 3, 4, 5 entries, 1, 2, 3, 4, 5 entries that we've learned from that routing table. We've added all of them to this routing table on a temporary basis because you already know that there will be problems and we need to sort those problems out. First problem is that we have 2 entries to get to node C. Here we can eliminate either one of them. We can't keep them both. The usual thing is to say, okay, we've learned something from node D here that wasn't really news to us. It's a cost of 3 units and we could already do it at 3 units. So we're going to scrap that line. However, it wouldn't make a difference if we just scrap that line because the costs in the end are equal. This example has again been chosen because it leads to such ambiguities. In most contexts, when you do exercises with this particular sort of calculation, then you will not get to such ambiguous situations. Let us get rid of that line that is bothering us, and it is gone. We can collapse our table a little bit, and we can see, are there any other problems? And yes, there is another problem. The old one, we can get to node E at a cost of 4 units. But we are at node E, so we can do it at 0 units. So also that line needs to be taken out, and it is gone. Collapse the table yet again, check for problems, and there's one further problem, namely that we can get to F with 2 alternative options right now. However, if you were to use that option, it's going to cost us 10 units, and the other one will only cost 2 units. So it's silly to even consider that one. That should not have gone into the table at all. So let's wipe it out and collapse our table to the normal size. What we've done now is we have updated the table at node E. We can continue this exercise, take table E and pass it on to node F, so that node F can calculate new roots and so on. But I think at this point it's becoming repetitive. You've seen how this works, and the only way in which you can really deal with this is to take your own little network and then do start sending packages from one neighbor to another neighbor in a random manner. Obviously, you can use the Dijkstra algorithm and the Bellman-Ford algorithm to calculate the roots for the same network, and that will tell you that you are applying the algorithms correctly. My hope is that the viewer who watched this video has gone through the cycle enough times to be able to apply the Bellman-Ford algorithm. I also hope that the viewer appreciates the manner in which it works. We have not touched on the correctness of this algorithm, or for that matter on the correctness of the Dijkstra algorithm. So that is something for viewers to consider. Why are these two algorithms correct? But for the purposes of our module, we can simply assume they are correct, and we will indeed use them in the protocols that perform root determination.